Ions. We learned earlier that atoms are more stable if they have the same number of electrons as an inert atom. In the first two rows or periods of the periodic table, the stable number of electrons is either 2 or 10, equaling the number of electrons of the inert elements helium or neon. We can extend that to the third row, in which the inert element is argon, with 18 electrons. Below, circled in purple, are the 13 elements in the first three periods and the second element of period 4, which can form covalent bonds. But what about these three elements, lithium, sodium, and potassium? They are the only elements which were not identified as being inert nor being able to make covalent bonds. Can they make any bonds? Let's start by studying lithium. Lithium has 3 electrons. Can you see the easiest way for it to achieve a stable number of electrons? 2, 10, or 18? Discuss. If lithium loses 1 electron, it would have 2, the stable number possessed by helium in period 1. Lithium would not become helium since it would still have 3 protons, but it would have the same number of electrons as helium. Since it would have fewer electrons than protons, it would have a positive electrical charge, making it a positive ion, a cation. Losing an electron transforms lithium from being an atom to being a positive ion, Li with a plus sign. Following that pattern, losing an electron transforms lithium from being an atom to a positive ion, sodium from being an atom to a positive ion, and potassium from being an atom to a positive ion. Group 2 atoms can form covalent bonds, but they can also form ions by losing electrons. In their case, they need to lose 2 electrons to become stable, as shown below. Can you predict what the charge of each of these ions will be? Losing 2 electrons transforms beryllium from being an atom to a positive ion, Be2+. Magnesium from being an atom to a positive ion, Mg2+, and calcium from being an atom to a positive ion, Ca2+. The electrons being lost by group 1 or 2 atoms need to go to another atom, an atom which attracts them more strongly than their original atom. Can you see any atoms below which could use 1 more electron to reach a stable number of electrons? Discuss. The 2 atoms circled below in group 17 would reach a stable electron configuration by accepting an electron. Fluorine would go from having 9 to 10 electrons, so would match the electron configuration of neon. Chlorine would go from 17 to 18 electrons, so would match the electron configuration of argon. Group 17 elements are called the halogens. Fluorine would have 10 electrons and an electron configuration like neon. It would still have 9 protons, so would still be fluorine. Since it would have more electrons than protons, it would have a negative charge, becoming a negative ion, an anion. Gaining an electron transforms fluorine from being an atom to being an ion, F-. Chlorine would have 18 electrons and an electron configuration like argon. It would still have 17 protons, so would still be chlorine. Since it would have more electrons than protons, it would have a negative charge, becoming a negative ion, an anion. Gaining an electron transforms chlorine from being an atom to being a negative ion, Cl-. Group 17, called the halogens, strongly attract electrons from other atoms, since they can reach the electron configuration of group 18, the inert elements, by adding 1 electron. Group 2 ions need to donate 2 electrons to group 17 atoms, but each group 17 atom can only accept 1 electron. So for each positive ion formed with a charge of +2, there will be 2 negative ions formed, each with a charge of -1. Group 1 atoms become stable by losing 1 electron, forming ions with a charge of +1. Group 2 atoms become stable by losing 2 electrons, forming ions with a charge of +2. Group 17 atoms become stable by gaining 1 electron, forming 1 or 2 ions with a charge of -1. The electric force is very powerful. A small imbalance in charge results in a very powerful attraction. An ionic bond forms when a group 1 or group 2 atom loses 1 or 2 electrons and becomes a positive ion. A group 17 atom gains an electron and becomes a negative ion. The two ions are strongly attracted and snap together, releasing a lot of energy. The released energy equals the energy of the ionic bond. This shows the progression of ions being created and an ionic bond being formed. Note the size change and the use of plus or minus superscripts to indicate a positive or negative ion. A fluorine atom takes an electron from a lithium atom, creating Li+ and F-. Notice the size changes. Li+ and F- have opposite charges indicated by the superscript of plus or minus. They attract and become stuck together by a powerful electric force. Ionic bonds do not form molecules. That is only done by covalent bonds. Ionic bonds create a material with a specific ratio of ions, but not a fixed number of ions. For instance, NaCl consists of 1 sodium ion for each chlorine ion, but that could be 1 each or 10,000 each. Only the ratio matters, not the numbers. With molecules, the numbers are fixed. For instance, a water molecule has 2 hydrogen atoms and 1 oxygen atom. A water molecule cannot be 4 hydrogen and 2 oxygen atoms. On the left is an image of an NaCl crystal, or salt crystal. On the right is a representation of the crystal with chlorine ions shown as green and sodium ions as purple. This is an extended structure in that it can include any number of ions as long as there's 1 Na for each Cl. When an ionic solid is placed in water, the polar water molecules separate the ions and hold them in solution. Each ion becomes solvated by water molecules, as the positive side of the water molecule is attracted to the negative chlorine ion, and the negative side to the positive sodium ion. This image shows the ions of table salt dissolving in water. Ions play important roles in living systems. Just like atoms which gain an electrical charge become ions, molecules which form with an electrical charge are polyatomic ions. Polyatomic ions are stable, like molecules, but have an electrical charge. They behave like an entity, not as just a group of atoms, since they're bonded together. Some common polyatomic ions are listed below. You don't need to memorize these, but should be aware of them as a few of them will be referenced in this course. Note that the indicated charge is for the entire polyatomic ion: phosphate, phosphite, nitrate, nitrite, hydroxide, hydronium, carbonate, and ammonium.